times. If you were absent in any lessons before this, I have put on Teams the videos of the lessons so you can go and watch them and just give me a shout if you need to ask any questions. So, we've done power, energy and time. We used a bulb in one of the experiments and we measured how much energy passed in a certain amount of time and we could work out the power of the bulb that way. There's a different way to work out the power of a bulb and it includes current and voltage. So different electrical appliances have different power ratings. Power is measured in units called watts, and a 100-watt light bulb is brighter than a 40-watt light bulb. A 100-watt bulb operating correctly transforms electrical energy into light and heat energy at the rate of 100 joules every second. A 40-watt transfers it at 40 joules every second. Okay, so the working power of any appliance depends on the potential difference across it, the voltage across it, and the current flowing through it when it's being used. So we're going to do this experiment here. So around the room, on each desk, there are 6 different wattages of light bulbs, so different powers of light bulbs. So you've all got one on your desk, but every single desk should have a different power of light bulb. Now, the way that you can tell what the power of the light bulb, the power rating is you look at the neck of the light bulb. And this one says 12 volts, 48 watts. That means you've got a 48-watt light bulb there. This one, some of them are easier to see than others. This one's 12 volts, 24 watts. Okay? So you read it off the neck. It might be that it's like indented in there, so you have to look really carefully, but it should be on the neck. So you are going to have to share the light bulbs. So once you're done with one, you can swap it with another group, or find another different one from the group. Okay. So what you're going to do, it's really simple, is you're going to set up this circuit. So you need a 12-volt power supply. So your power supply needs to be on 12 volts. An ammeter in series with your bulb, and then a voltmeter in parallel with it. And I've put, as usual, a picture of the setup in my PowerPoint. So we've got an ammeter connected to a bulb and back up to the power supply. The power supply is on 12 volts. And then your 2 wires coming out from the bulb to your voltmeter. Okay. I'll put that back up again when you're setting it up. So what you're going to do, well, it's really simple. You just read off what the current and voltage is for your lamp. So for example, if your lamp is let's say I've just got an example here, a 24, if that's what it says on the neck, then your potential difference across the bulb might be 12. Your current might be, I've got an example here, 1.7 amps. And then your last one is current times voltage. So it's 12 times by 1.7 for that one. I know there are only 3 rows there, but I think there should be 6 different wattages of light bulbs around the room. So you can do this 6 times if we have time. Okay. You just need to cooperate with other groups and find the ones that you haven't done yet. Okay. So it's a really simple experiment. Anyone have any questions before we start? Wires and ammeters and voltmeters are at the side of your desk as usual. On you go. Okay, so hopefully we should be seeing that the current times by the voltage is similar to the manufacturer's power rating. As Daniel was pointing out, they're not the same, but they won't be the same because although it says it's 48 watts, light bulb efficiency is really quite low, so you're not going to get as much as the power rating. But you should be getting a ballpark. So you can see that 24 and 21 is all right, 48 and 42, 36 and 31. If you're getting 36 and you're getting 5, then there's an issue there. But if you're getting sort of in the 30s, that's not too bad. Okay, so current times by voltage is equal to the power of an electrical item. So in conclusion, within experimental error, the product current times by voltage is the same as the power rating. So P equals IV. So P is the power in watts, I is the current in amperes, and V is the voltage or the potential difference. Difference in volts V. Okay, so experimentally, we've proved that equation. You can also derive mathematically the equation from equations that we already know. So you can see the formula can also be derived using three other formula. P equals E over T, which is what we came across last lesson and also when we did the energy booklet. Work done, or energy, electrical energy, is the charge times by the voltage, which you did in electricity 1. And charge is current times time, which you also did in electricity 1. So these three equations you have come across. If they're not very unfamiliar to you, you might want to go back and have a look at electricity 1. So if we substitute equation 3 into equation 2, so that means we're replacing the Q in equation 2 with IT, because Q equals IT. So E, that W is energy. So energy equals IT times by V. Now we need to substitute that equation into P equals E over T. So we're replacing the E with ITV. And then we can cancel those T's out. So we're left with P equals IV. It's actually quite a nice equation to use. If you like triangles, you can put P on the top and IV at the bottom. But obviously it's only 3 terms. You just need to watch the units when you're using it, as always in National Fire. So make sure you've got the correct units when you're putting the numbers in. So there's a few examples on the next page. You can start having a read through it, just while I leave that for a second. Feel free to have a go. Okay. So, power, current, and voltage examples. Best thing to do, write down everything that's given to you in the question and then put it into the equation. So, small torches are rated at 2.5 volts. So, V, 2.5 volts, 0.2 amps. So, the current (0.2 amps). What is the power of these lamps? So power equals question mark. So we're going to do P equals IV. So it's already in amps and it's in voltage, so we don't need to change any of the units. So it's 0.2 times by 2.5. And that comes to 0.5 watts. Number 2. The full beam headlight on a car is rated at 48 watts and the dip beam headlight is rated at 21 watts. The potential difference of a car battery is usually about 12 volts. Calculate the current in the full beam and the dip beam. So have a go at that. So the power is changing, you're going to find the current. So we're using P equals IV for both of these, but they've got different powers. So for the full beam one, the power is 48 watts. So that equals the current times by the voltage, which is the same for both of them, which is 12 volts. So the current is going to be 48 divided by 12, which is 4 amps. And for the dipped beam one, the power is 21. Current is what we want to find. And the voltage is again 12 volts. So the current is going to be 21 divided by 12, which is 1.75 amps. Okay, just getting into the exam sort of way of writing things down, equation, units, or equation numbers, answer in a unit. Okay, number 3, the power of a heater is 1 kilowatt. The current in the element is 4.4 amps. Calculate the potential difference across the element. So again, have a think about that one before I go through it. What's your unit? So it's 1 kilowatts, so we need to change it into watts. So how many watts is it? Sorry? Yep, exactly. 4.4 amps, and we want to know the voltage. So it's going to be 1,000 equals 4.4 times by the voltage. So the voltage is going to be 1,000 divided by 4.4, which comes to 227 volts. Okay. Right, I'm going